Okay, so shielded metal arc welding, commonly referred to as stick welding most of the time. We're trying to get away from that. We're trying to make sure that we use the technical terms for a couple of reasons. Number one, it can be confusing. There's a lot of stick electrodes for all processes. And that's actually why they switched the abbreviations with the full terminology, because if you see it on a print and you just put stick weld, somebody maybe from a different industry might be referring to that as thinking you just need to be able to abrase it or stick it with a TIG function even, right? Versus SMAW. Number one, the last two tell you exactly what type of process it is. It's arc welding or, say for example, resistance welding is a completely different type of welding process. We use electricity, but it's also off of pressure. Now, chemical welding can be different. If you look in the first page of chapter 3, it tells you all the different types of welding and joining processes. Naturally, there's arc welding, soldering, oxy-fuel gas welding, brazing, solid state welding, resistance welding, and other welding and joining processes, which include adhesive bonding. Okay, most of us don't think of adhesive bonding as a type of weld. Once you think of JB Weld, it actually can be considered a type of welding process. To what extent, that varies very much as we're going through this, okay? So back to SMAW, shielded metal arc welding. Okay, so we got a metal electrode, stick as you might say, that's shielded, has flux core around it. We're using the arc electricity to get there. In this situation you can see, so you can see a lot of pictures like this, and it's going to ask you to depict what type of process this is for maybe this picture. So a couple things we can see. We've got the base metal. Number one, we've got a core wire. We've got an electrode covering our flux, which is consisted of many chemicals, including our alloy, the weld pool. But then right here, specifically for this one, it's a solidified slag. So if I seen something like this with the slag, I'm naturally already going to know that it's one of two processes, is what I'm going to assume, either SMAW or flux core arc welding. Because most other procedures may be submerged arc welding. But something that produces a slag, okay? I know it's not GTAW, and I know it's not a GMAW process because they don't traditionally use or have a solidified slag at the end of that, okay? So I want to read a couple things from the book here. It's on page 3-4, 3-5, left-hand column, top portion of this, if you're following along with the book. Third paragraph down. The primary element of the shielded metal arc welding process is the electrode itself. It's made up of a metal core wire covered with a layer of granular flux held in place by some type of bonding agent. All carbon and low alloy steel electrodes are essentially the same type of steel core wire, a low carbon rimmed steel. Okay? Any alloying is provided from the coating. So again, stainless is a different situation. That metal is different. But most, what it's saying here is all carbon and low alloy steel electrodes, low alloy, have the same core. And so that way it's consistent. Okay, so if they're using the same steel core, let's just say 836, mild steel, okay? Then they can make sure it's easier for them to have that as a base of a formula and then add the other chemicals around it when they're doing maybe a carbon equivalency problem, or they're trying to figure out what the tensile is or what the corrosion is. This factor of the electrode is consistent, and it makes it easier for them to be able to spec and engineer the flux coating around that core material being the same or consistent. Okay, and it's really important to know. 6010, 7018, it's the same electrode. 11018, it's the same electrode core wire. Okay. The rest of the material, the higher carbon, the chromium, the magnesium, aluminum, things like that, are all added in the outside flux covering, okay? And at different temperatures to boot. So a couple things that we don't have a slide for it. Before we break into that, I want to talk about 5 things that's always happening when we are actually welding in a shielded metal arc welding process. Number 1 is we're shielding. Okay, we've got a shielding gas, we're doing shielding, is always happening. We're deoxidizing, so you've heard me in the booth talk a lot about let that slag do what it's designed to do. It's going to dig into the base metal, it's going to bring all the impurities and all the bad oxides to the surface. If you're going too fast, it's not gonna allow that flux to do its job and bring everything to the surface the way it's supposed to, okay? Number 3 is we're alloying. We just talked about it. We're introducing all those things in the weld pool. And we talk about consistency, and the important thing about when we do that is it also makes it uniform. So when we pour things, or we have a foundry, we've been through chapter 3, we talk about blooms, slabs, billets, and blooms, right? And everything comes out and disperses in an even pattern when it's in a liquid state, to a certain extent. That's something that we're doing. We're not going to get too crazy into the physics of that, but I want you to think it's much easier for us to control in a liquid state to where it disperses evenly versus all the chromium stay to one side of the electrode, okay? Or all the carbon stay to one side, because then that's going to create a really high tensile spot over here and a little bit more corrosion resistance over here, and maybe in the center we've lost all strength, so there's the weak link. So when we do this alloying or adding the flux in, we want to make sure we do it in a liquid state. So that way it disperses evenly upon how gravity pulls it, okay? So this is also really important. We're talking about what position of welding we're doing too, okay? So keeping it a nice liquid puddle in certain stages, keeping the heat up to where you're not shocking the system and the metal, so to say. And we'll talk a little bit more about that during like martensitic and bainite, some of the tempering processes and what we're creating during the grain structure, okay? So those are the first 3 things: shielding, deoxidization, alloying. Now let's do ionizing, okay? Ionizing is when the flux coating becomes molten. It improves electrical characteristics to increase arc stability. So it makes a smoother arc. For us as welders, sometimes it makes it easier for us to be able to weld it. So I mean, certain rods are easier to weld vertical than others, right? And you'll find out as you get to welding, there's certain brands you like better. It's almost like they weld better vertical than other ones. Certain flux cores weld better vertical than other positions. And maybe you don't do a lot of vertical. Maybe your facility only does a lot of flat and horizontal. That's what you want to focus on. But if you're going to be doing a lot of vertical positions, then you usually want to be focusing on an electrode that might be better for you to achieve more successful welds in a vertical position. Not because you have bad welders, but number 1, it's time and money. And the more problems you have, the stronger, or the more setbacks you'll have. It means more money, more lost money. The job's going to be behind. Everything else is going to be affected by doing that. Us from the inspector side, what's really important for us is to know, the good thing is if we know which ones weld the problems they have, and out of position welds, is tremendous for us to be able to know that and go forward. So for example, I know, and you've heard me say several times, that 7018 332 electrodes are very susceptible to starting porosity, right? So make sure to get them out of the rod oven. If I see a lot of 7018 332 electrodes on the ground when I go into a job, number 1, I'm going to look at x-ray, but I'm going to be looking at all my starts and stops and looking for a lot of porosity. I already know the issues before I even get there. Before I can even start to see them, I know the problem areas that I want to be looking for as an inspector, so that this bridge doesn't fail and collapse on somebody or a building or anything else. That's the important part of being an inspector, is knowing the limitations of these processes, the filler metals, what they're good with, what they're not good with. And that's where also our background in welding helps us out as well. And then number 5 is insulating. So naturally this solidified slag insulates that, and it lets it kind of cool down and temper itself a little bit so it's not shocked, particularly outside with maybe a cold wind. So, you know, most of you know I'm from southwest Wyoming, and even here in central Oregon, we can see a 70-degree temperature in the middle of the day, or even a 60, and then all of a sudden turn to 10 below at night, right? And then by the time we pick up a wind chill, a greater part of the United States, especially the northern part, you can start to see 10 below with the wind chill pattern, and this insulation, or this blanket of slag, is creating insulation there. So you're not shocking that system and tempering, or I'm sorry, hardening that outside surface of that weld. So it blankets it, lets it do what it's designed to do, make sure it cools down in between, and then you chip the slag off and let it go from there. Okay? So 5 things: shielding, deoxidizing, alloying, ionizing, insulating. Those are the 5 things that are happening in this process particularly, okay? Next page, we talk a little bit about The American Welding Society specifications a 5.1 and 5.5. You need to know that. They are the regulations. They describe the requirements for carbon and low alloy steel electrodes, a 5.1 and a 5.5. Okay? Excuse me. All right, so now we're going to start talking about the electrode identification system. Most of you have dealt with this at this point, but when we get into weld inspection technology, every little thing tells us something, and it's really important. Number one, it tells us it's an electrode to start with, right? We'll talk when is it not. When we get into SMA or submerged arc welding, the first section starts with F because it's the flux. Okay. Second part is actually going to be the E for the electrode. The number 2 for SMAW is actually the strength. Okay. The first 2 after electrode. It's not always the first 2. It can be the first 3 as well. Whether you have a 70-18 or a 110-18, the first 2 or 3 tell you the tensile strength of this position. So, the minimum tensile strength of this electrode. Okay? So that's also important as well. It can be higher than this. Say the tensile strength of this 70-18, this batch that was poured, right? Or this flux got a little bit off, say it's 0.001% extra carbon. And it still falls within the Sharpie V-notch requirements and everything else. Then that tensile strength might actually be 75 or 76,000. What all it's saying the requirements for it at this point are, that's the minimum tensile. It cannot drop below 70,000. So 60-10, 60 is the minimum tensile there too. It's actually closer to around 66, 67. So 60-10 5P plus, what we run 66, 67. You get down to the traditional 60-10, which is a red. The tensile strength's down around like 62, 63. But it doesn't have some of the flux, some of the corrosion resistance and so forth in it that some petrochemical companies want to require within their materials also. Okay. All right, those are the first 2. The third one is actually going to be the position. So I don't want you to think of it as the third one. I want you to think of it as the second to last. Okay? Second to last is going to be your position. So for example, 70-18, 1 is an all-position electrode. Okay? 2 is used in flat and horizontal fillet welds only. So flat, fillet, or groove. But horizontal, only fillet welds. It cannot be used in a groove weld because it's a very viscous or liquidy, fluidy puddle to where you have a chance of it running down as well as lack of fusion on the bottom side of that weld. Okay. Number 3, it's not used at the present time, but number 4 is used for a downhill progression only. So I have very rarely seen a 70-48 rod. Well, actually, I've never seen it. I've heard that they make them. I don't know. I've never looked at it, but I've never seen a 4 progression or position electrode. I've seen a lot of 1s, and then basically you start to know which electrodes you can and can't use in what position. So for example, 60-10 can be an uphill or a downhill electrode, right? It tells you that. But 70-18 is not. So it's a low hydrogen. It ends in a 5, 6, or an 8. Then it's an uphill rod only, unless it's stamped for a downhill or it's a 4. Again, I've never physically seen one. I have heard they exist, and they're even in the books. But I have never seen one. I imagine they're probably someone of a special order at this time. Okay. Moving on to the last one. The last one is the coating and the operating characteristics. So this tells us, number 1, the flux capacitor. Sorry, it's going back to the future there. The flux makeup and components, as well as what type of polarity and what type of current, whether it be alternating current or direct current, and then are we using electrode positive versus electrode negative. And if you don't know the difference between reverse and straight polarity, let me know. We need to talk about that, right? So straight polarity, typically I want to think straight line, straight bar, negative terminal. So DC electrode negative is my straight polarity. My positive is actually reverse polarity. My ground and positive are going in different directions than we originally thought, okay? Instead of going from positive to negative, the way electricity works is it actually goes from negative to positive, all right? So the negative electrode holder going to a positive workpiece is considered straight polarity, but what we do with 718 and 6010 is a reverse polarity. Electrode positive going to the negative ground workpiece, okay? That is reverse polarity. All right, we talked a little bit about electrode coating classification. These are F numbers, and I think most of you are probably like, oh, that's where it comes in. Now we're talking about it. Weld 1 and Weld 2, we start talking a little bit about F numbers. I tell you, don't hang up on them too much, because this is specific to AWS only. As me and everybody else usually use a spec, so whether it's an A5.1 number, those first things I talked about that are defined in AWS, A5.1 and 5.5, what's the spec, what's the class, and everything else. So we get into that in Module 5 when we start talking about writing out the procedure, okay? But basically, I like to keep this one on here for sure, is what they're saying, what AWS is saying is that this is supposed to be the easiest electrode, harder, harder, and hardest, okay? Now, if you notice, 5, 6, and 8 are in the F4 position, all right? So, what this means is that these three are supposed to be the hardest to weld with, and some of you know that running uphill 6010 is one of your biggest nightmares ever, including mine as well, right? But if you also, I want you to notice, what do these three numbers symbolize? Again, low hydrogen electrodes. We get on page 3-6, you can look up the significance of the last digit of the SMAW identification. All right, I'll try to do this here where you can see it. And right here, it tells you a little bit more about the classification, what the current is, what the alternating current, the description, and so forth. And you can see some of my highlighted items. Number 1, 5, 6, and 8 are all low hydrogen, okay? All right. And then here in a little bit, we're going to talk into this section right here about steel alloy suffixes for SMAW electrodes as well. Okay? All right, so moving on. Low hydrogen electrodes, here we talked about 5, 6, and 8. Purchase in sealed metal containers. They store after opening in a heated vented oven. Limit atmospheric exposure. Now most places like Central Oregon where there's a lot of sunshine, it's not super humid. Wyoming, Montana, Idaho, Colorado, New Mexico, you're not going to have to worry about it as much. You can open up a box of electrodes and typically you'll be okay for, to weld with them for the day. All right, but when you're done with them at that point, you want to get them in there. If it's strict by code, it's no more than 4 hours. After 4 hours of exposure, you want to get them in there. But if it's raining, get them in there right away and just keep them locked up, okay? A couple things you can do. Now the heated rod ovens are pretty accessible, and then they also have these plastic containers that you can put them in and seal them up, and then you can charge them with nitrogen if you're on a different job location and so forth. Make sure you're communicating with your QC person how they want you to handle low hydrogen electrodes on the job. Naturally, if you're welding in Portland in the winter months or Seattle where it's raining 24/7, you're probably going to need to have a little bit of a covering or something to help protect you while you're welding and using these electrodes. Okay? All right. Moving on, here we talk about the suffixes. A1, B1, B4, W is for weathering, okay? So, here's some really cool stuff. So I want you to think about, we talk a little bit more metallurgy, and this is where we do this, and you may have heard me talk in some of my other videos about joining like AR400 plate to soft steel or mild steel, right? Because we need, certain situations, we need a cushion, and then in certain situations, we also need a hardened steel. So I'm going to shut this down here in a second and draw a picture. But I want you to look right here. So C1 has 2.5% nickel, okay? C2 has 3.5% nickel. Some of these alloying elements help us understand exactly what we want to achieve. Sorry, I lost my train of thought there for a second. Some of these alloying elements within there tell us how we help bond two different pieces of material together, okay? So I'm going to use a rock crusher for an example, okay? This is what we call a spider on a rock crusher. And on this spider we have these big cast things, okay? And the first primary rock crusher usually has these big kind of shark looking fins here, so they take a big rock and they knock them down into smaller rocks, okay? And then this might be your first set of rollers, and then your second set of rollers, naturally these get smaller, okay? And then this is joined together, this big cast piece of steel, the bolt comes through here, bolts on, and this one might have a smaller pattern, okay? And a little bit different geometry to help break up that rock to even a smaller, smoother surface as well. Because as you know, we don't want all rocks to be jagged. Landscaping rocks, things we might be walking on, we want it to be a smooth rock, right? So we can achieve that by running it through the right types of rollers with the right prep in there, knocking some of the edges off, tumbling on other situations like that. And then these ones might be a very fine-toothed situation, okay? Now here's our bolt that holds these on. Okay, it's usually a very high tensile strength bolt, which we'll talk about this later on as we get into tensile and yield of what we need. But specifically for this one, I want you to think of this. There's the center, there's a shaft here, and a big pulley system that a big motor turns in order to drop the rock down into the chute work. And then it gets transferred down here, and as it comes in, this rolls and rotates and crushes it all up, okay? Now number one, the part that's in contact with the rock needs to be a very, not necessarily very brittle, but a very hard material, okay? If it's too brittle and the rock's too hard, then it's just going to break off in big pieces, which isn't what we want. We want something with a high tensile strength that's resistant to abrasion, particularly because rock is very hard, okay? So you might hear of some things like a diamond bit, stuff like that would be one way to do that. But if we tried to do that for rock, we'd spend more time just breaking off the chips. It would just be a very long and lengthy time process. We use large pieces of metal, multi-stages of this, and that way it goes a lot smoother and faster to process a large amount of volume, so to say, okay? However, so this piece right here is cast. This is harder, okay? This is the hardest out here. So high tensile strength, it's the hardest. And in the middle, it might be, let's just give it a middle. Let's give it just say the middle, okay? It's not quite as hard as the hardener, but it's the middle. And then right here in this section, this is the soft piece. This is more like your normal mild steel, maybe just a little bit harder than that, okay? Because it is seeing a lot of vibration, but this has to have a lot of give as well. Because if a rock gets stuck here, number one, the belts would slip, but we don't want this thing to break here in the middle because it would take a long time to replace the shaft, the spider, and everything else. And these are usually, by the way, about 10 feet long, okay? 6 to 10 feet long. And about 2,500 pounds per piece. Naturally, you'd want these have to be balanced and vibration and all sorts of other stuff too, okay? That's a whole other topic for another class. But what we need to do is we need to be able to pull these off, so if this stuff breaks down, what we can do is, typically what we would do is about every week or so, you'd come in and you have a shutdown day and then you'd build these back up. So you could pop the chute back off, you could come in and you could put studi or a hard facing rod on the top 1/4 inch of a surface, and this eliminates downtime. And it also eliminates from you having to switch these out, which may be an 8-hour process, or let's say